we're slipping onto an entirely different concept of flow now, using one of Mark's more beautifully constructed titles, Circadian Rhythms and the Flow of Biological Time. I'm not even going to attempt to introduce this. I'm going to ask Ben to do so. So, Benjamin Smarr, sorry, I should add, postdoctoral fellow at UC Berkeley. And you've been looking, at the context of the biology and the way that we understand flows within that context.
Sure. So it's actually really fun hearing all of these talks, last night and this morning, that fit unbelievably well into how I think about biology. And I think a way that we should think about biology more, which is if you think about your body as the world, and you have these different organs that are sending information flows to each other all the time, you can do a lot of the same sort of GDP modeling to think about how stable is the structure of those flows in my body. And those flows are what let you develop, what give you health. And so for an example, rather than looking at what temperature are you once a day, once a year, you have a fever or you don't, if we look at the shape of that flow of temperature across your body between organ systems, that flow is carrying information. So circadian rhythms is an instance of a kind of what I call temporal structure, where that is to say the flow is not random, there's shapes to it. There's a day, and every day you get this nice repetition.
A wavelength.
A wavelength, exactly. And there's many different scales of wavelength in these flows, but you have all these different countries in your world body, if you will, that when they synchronize, when they have a similar wavelength and phase lock, they know how to anticipate each other, they react intelligently, efficiently, and you're healthy. You digest things when you're supposed to, and you metabolize when you're supposed to, and you heal when you're supposed to, you remember when you're supposed to. And that's very dependent on the right time domains synchronizing across these systems in your body. And so thinking about not just what's in my body, what's the nutrient or what's the hormone, but where am I in that flow of information through my body, and is that flow synchronized to the other flows? It really gives you a much meatier insight into what's going on physiologically, and is that good or not, right? Are you going to be getting cancer years from now because I can see a perturbation in the flow so that the shape of these things is now a little bit different today than it was?
So very specifically, concrete terms, what are the metrics for this flow? How do we measure it? Where do we measure it?
That's the question that I spend a lot of my time trying to work on.
Okay.
It's exactly that. So, I'm a big fan of body temperature in part just because it's really easy to measure, right? I can slap a little thermal sensor on you. I tend to wear a bunch of them and sleep deprive myself or eat a meal or whatever. And the reason is it's really difficult to look at all these internal flows, right? You have, depending on whom you ask, many, many dozens to many, many hundreds to many, many thousands of channels of information flowing through you, different proteins in your blood or different hormones, sugar levels, all kinds of signal information that your organs are trying to process. But a lot of them share a common output. So we've been talking about data triage as one of the ways to make flow computing possible when you have this overwhelming wave of data, right? And your body has way too many channels to monitor all of them simultaneously and make a lot of sense out of it intuitively. But, sex hormones like estrogens and testosterone, and arousal and wakefulness hormones like cortisol, and metabolic cues like insulin or blood glucose, a lot of these things tie into changes in body temperature, and it's through changes in blood flow or changes in metabolism. And circadian rhythms are another one of these core modulators. Time of day changes your temperature. You're warmer in the day, and then you get cold at night. And so if we can sort of understand how are these different internal systems that I would have to take your blood to look at, how are they impacting temperature in a systematic way, then by taking something like body temperature, we can sort of tap into a whole bunch of flows at once. And then we have this data modeling problem of how do I back out multiple different channels from this signal.
So if you knew what my temperature was when I woke up in the morning, and my temperature at midday, and my temperature in the evening, you'd be getting a picture of that wave flow in my body across a 24-hour period, and that would give you a form of data, a form of information or understanding about how my biology is functioning.
Exactly. And that's very informative for, I'm going to simplify all of biology into health, but for example, if the amplitude of that wave was shrinking as you were aging, that would give me a good indicator that you're much more likely to suffer cognitive decline at an early age. That this rhythmic structure that allows your organs to work with each other in a synchronized way is falling apart. And so the amplitude is therefore sort of flattening out.
So is there an ideal wavelength?
Well, that's a really great question, right? So circadian rhythms is one of these wavelengths that has evolved to match the environment, because the environment is also not random, right? So we have days, we have years. To the extent that it's random, you have to be able to react, but to the extent that you can predict some of it, then you can get ahead of those changes, right? So days are great, years are great, social rhythms within your own species are great. So for example, menstrual cycles, ovulatory cycles, if you're a cicada, reproductive cycles every prime number of years. And I think the real question is, within each of those temporal scales, what's actually the shape of the thing at high enough temporal resolution that we can really see the signal? So that is to say, yes, there's a circadian wave, but is it doing this, or is it doing this, right? Or is it just doing this? Is it going like this? Those are all very different states, right? And depending on the system, they may or may not be healthy. And so that's the big thing that I'm actually just really excited about all the time, is figuring out how do we start to measure all of those different systems at enough resolution that we can now really see the information that they're carrying.
Is temperature the only metric here?
No, not at all.
What are the other ones you're thinking?
Well, I mean, any biomarker system, right? So if you were looking at changes in cortisol concentration, it sort of goes up at the end of the night to wake you up, and then it comes down during the day. But it's also doing a lot of what we call ultradian rhythms, so faster than a day rhythms. And what is the change in amplitude of those little rhythms that make up this larger rhythm? How regular are they? Those things are also, it appears to be, and this is new research that I'm trying to drive, but it appears to be the case that all of these systems really do interact. So it's exactly like Mark was saying. I couldn't have possibly set this up better for biology, in fact. It's flows and interactions. And when my cortisol is changing, it's trying to inform my pancreas about whether or not to be making insulin, in part. It's trying to be informing parts of my brain. Should I want to feel hungry or not? Should food seem exciting or not? And all of that interaction allows me to then either give myself ulcers or digest healthily and move on in the day.
So this is predictive measurements. I mean, on the whole, the value of this, right? Obviously, you be my physician, you could measure all kinds of things that might, without looking at flows, you could establish all of those things already using other measurements. But this measurement, you're saying you believe will tap into understanding, preventing future illnesses and diseases, cancers, as you say, ulcers, whatever it might be.
Exactly, and I think an analogy that I like is it's not necessarily that it's which biomarker are you looking at. Is it temperature? Is it a hormone? Is it number of steps you got when? But it's understanding that time really matters in biology, right? That seeing it not as what is the biomarker, but what is the flow of that the rate of change over time is very informative. And I think Mark actually gave me this analogy when we were talking on the phone earlier, but sort of thinking about radios, right? If I said, what is the amplitude of radio wave in this room, and I measured that once or twice a day, I would kind of see something. But I would do that until I was dead, and I would never understand that I was trying to listen to music, right? And only once I had sufficiently high resolution and I could see the changes in that frequency could I say, oh my God, there's all this information in the air that I was just completely missing, right? And that information allows me to make predictions. So to give you a concrete example, I put out a paper recently about doing monitoring pregnancy in mice, which is as exciting as it sounds. But I'm doing a lot of work in how the temporal stability, this internal synchrony, is really important in development. And and we can come back to that. But as a result, I was breeding a lot of mice, and scientists tend to do this when they're doing lab work, right? And the state of the art is sort of standard practice is mice pregnancies last for 3 weeks. So you pair your mouse and play some jazz or whatever, and then 2 weeks later, if you sort of pick the thing up and weigh it, it's on average a little bit heavier, and that's how you know that 1 week later it's going to give birth, right? So 2/3 of the way through the pregnancy, you can start to detect it. And what I discovered was by using these temperature probes that the mouse could just walk around wearing this thing and I didn't have to handle it at all. Within about sort of 8 to 12 hours of them mating, I could tell with 100% accuracy that they were pregnant or not. And within the same time window, the first, still within the first day of when they've mated, was that pregnancy in fact going to come to term, or sometime in the intervening pregnancy was there going to be a complication and the mouse would do what they call reabsorbing the fetuses. So something has gone wrong, and the mouse says, you know what, I better save the energy and try again next time, because mice breed frequently, they do this. And we had no idea I had no idea that was even possible. I didn't start out looking for that. But I was looking at these flows of temperature, just sort of day by day by day by day across the pregnancy, and very frustrated that sometimes I would invest all this time in mice who then wouldn't actually give birth after all, and saying, what can I just see, exactly like we were saying the visualizations, what can I just see in the data that give me an intuition about whether I could predict this outcome? And it was clear as day, once I had sort of gotten my head into the space, that you could see it wasn't how cold is the animal or how hot is the animal, but if you looked at the shape of that daily curve, there were these frequencies of colder moments that just give you this very high accurate prediction of this pregnancy is going to take. And if they were missing that higher frequency bit, even if on average they look the same, that higher frequency bit says this pregnancy is going to work. And you don't have it, I already know 3 weeks from now you're not going to give me the pups, I don't have to waste my time. So figuring out can we get that sort of thing into humans, of course, is very exciting. Right? And it's not that we know what we're going to predict, it's just that we have access to a ton of information about are the flows in your body changing in some way that indicates in the future something's going to be different than it is.
I know we've got a lot of people here who are in different ways involved in diagnostics, medical, biotech, all kinds. Anybody has a question, there's a microphone just there. You can step up towards it. Presumably then, this is in its infancy, this kind of research for you, right? And I don't know how many others are in similar fields, but presumably, we are now, as we sit here, only just guessing at the ambit of the predictive potential of this kind of tech. I mean, do you have any specific, concrete intimations of what this kind of, if we could cover people, what we would learn from this?
I think basically the sky is the limit, and I can give you a few examples of why I feel that way. If you have a fever, your temperature is higher, right? It had to get there. So looking at how far ahead of that rate of change can we get means I don't know that 2 weeks ahead of you getting the flu, I can predict you're going to have gotten the flu. That's probably impossible. You don't have the virus in you yet. But the night before you feel sick, can I say, you know what, tomorrow night you're going to really feel sick. Maybe you shouldn't go to work, or maybe take some vitamin C, get some sleep, whatever it would be, right? It's definitely the case that right now medicine is based on recognizing that you're broken sufficient that it's obvious to you that you're too broken to pretend it isn't the case, and then you go to the doctor, right? So can we get ahead of that in every medical field? Yeah, definitely, right? Like I said, if you're going to have dementia later in life, the amplitude of this circadian rhythm, whatever mode you're looking at it, is likely to have sort of fallen apart, and therefore the amplitude has come down, the coherence is gone. So you're getting lots of bouts of sleep as you age, for example, instead of a consolidated night.
And clearly forecasting dementia is something where we think.
And forecasting dementia or loss of bone density or any of these things that one wants to avoid, right? By the time you've noticed it, that change has been happening for a long time. So it's really a question of, with a high enough resolution, in time, high enough resolution of any of these metrics, can we see things that indicate that change starting rather than it's at an endpoint and you have a disease?
So it's time to refine the kit that we're putting on our wrists, right?
Exactly. So that's part of the work, is working with engineers to get better armband, for example. Yes?
Thanks so much. It's fantastic. So one of the things that sort of hampered the study of flows and time series in biology has been the expense of making measurements.
Yes.
Right? So 2 years ago, for instance, to measure a whole transcriptome, to see what all the genes in a genome were doing quantitatively, it cost us about $500. A year ago, it cost about $250. Today, it costs about $120. In a year, it's going to cost $15. And that's really changing the landscape of molecular biology, right? So now, in addition to having very inexpensive time series or flow measurements that you can wear on your wrist, you're going to have molecular measurements that you make of the system. So can you speculate a bit on how the availability of very dense and very rich time courses of molecular measurements will impact the sort of work and the sort of things you're thinking about?
That's a terrific question. And I think the systems integration, going from what my dad would focus on, the microbiome probably, right, to your own metabolomics, endocrinology, whatever, to how is that manifesting in changes of behavior, changes of some obvious output like temperature, sleep quality. I think that's absolutely critical. And I think the thing we're going to find is that there's a lot of heterogeneity in the population that we have been completely squishing together by saying, temperature should be 98.6. Why? Well, because 50 years ago, I took a group of sort of 40-year-old white males, and they had this range, and I took the mean, and now that's canon, right? And so that makes that much less useful comparing you and me, right? And there's all of these, for example, sex differences or ethnicity differences, just genetically based differences. So I think the more of that system we can map, the more we can start to understand where are those salient pieces of information for whom that then give me predictive power of some outcome that I care about, right? And until we have that information, it's really hard to make really personalized predictions. And so that's merging those levels is, I think, totally critical to this.
So I have to follow up one very short thing, and then I'll get out of the way because there's a line. So that you made a great point there. So the example of sex and ethnic differences, those are sort of hypotheses that we can go at. But of course, when you have all this molecular information, you may not know a priori what the cluster look like. Do you think that you have the maths and the statistics and the computer science that you need, or into the community at large, to discover those without a priori knowledge?
That's a terrific question, and I think it's exactly right? We have these categories of, like sex is a completely made-up category, right? But you look in my brain sort of like I can classify as a man, and so that's how I make a binary out of a very complex space. Ethnicity is obviously similar, age is similar. There's going to be a lot of structure that we couldn't have intuited, right? And there's going to be a lot of structure that we think we've intuited that's just wrong. And I definitely don't. My hope is that we can build those tools, right? And I think it's an iterative process. As we find the data, we can start to say, sort of like I asked to the visualization group, how do we intelligently winnow through all of those flows to pull out, dust away the rest of the marble to pull out the statue, as they say, right?
This is great information. There's a particular flow, biological flow, that's been studied for thousands of years, which is the Eastern Qi.
Okay.
And what I was wondering is what your take is on Qi, whether that has any connection and whether we'll ever be able to measure something like that connected to what we do.
Yeah, I think that's a great question. And I think it gets to the previous question, in fact. I think there's a lot of biological structure that we don't know about. I've never studied Qi. I wouldn't know how to quantify Qi, but I think there's a lot of folkloric knowledge that is sort of saying, hey, I think there's a pattern here. And when you bring it into a modern Western medicine context, a lot of that just gets dismissed because it doesn't match expectations. And so I think the question would be, what if you're a Qi specialist, whatever that is, right? How can you work with people like me or sensor engineers to find those changes in the physiology that match what you're calling Qi, so that we can agree on what we're measuring and move forward, right?
And beyond medicine, presumably psychology.
Yes.
And psychiatric treatment.
Yes. Well, and so the work I'm really focusing on now is, in fact, early development, because what I've found is that disrupting the temporal structure in utero, so when the little fetus is developing, and again, this is mice that we're now trying to figure out in humans also, but mice live a lot faster. I can see a whole lifetime in a mouse and can't do it in people so easy. But if that temporal structure is disrupted in utero, so the mom is being jet lagged like she was a shift worker or traveling a lot, the behavior of the offspring, once they come out and grow up under a normal 24-hour day the rest of their life, is permanently changed. And they're anxious and they're antisocial and they're sort of fixative and look a little bit ADHD-ish.
You're spotting this in mice.
I'm sorry?
Are you spotting this in mice already?
Yeah.
You're spotting the mood impact.
Well, and exactly how you translate a mouse's propensity to explore a new maze or a new object into human psychology is difficult, right?
Yeah.
Obviously, humans do that a bit more complexly, and at least in a way I can intuit. But the point is, these early disruptions have a long-lasting impact on behavior and psychology. So I'm really interested. Health is one thing, but I think it includes not just mental health, but really mental optimization, which is education. And so thinking about when should you be taking classes? Is it right to make kids get up early in the morning when, as puberty hits, your sex hormones tend to delay your circadian clock? But I'm making you get up super early in the morning because that's when factory schedules were, and now you have to pretend that you're not jet lagged every single day. And lo and behold, you hate your teacher, you hate school, you don't learn anything, right? That's a failure to understand that the temporal structure is part of the biology, right? It's like saying, well, wood is cheap, why don't we just make people eat wood? It's just not going to work with your physiology, right? So understanding that temporal structure to do things like better education, more personalized education, I think gets into the whole world rather than just, I want to not have cancer, which is true, but which is really a subcategory.
Sorry, I've held you there. Please, your question.
Yeah, this is so interesting. Thank you so much. Have our societies around the globe are going to be facing a situation of demographics that will could benefit tremendously from your insights into this, and that is aging and end of life. Many people would prefer to have a squared morbidity curve, and this could give us potential to control and have autonomy in how we shape that squared. So we're very healthy, then we have a little bit of time to say goodbye before everything shuts down and we go to a multiverse. Have you run into this before? What is your plan as these questions arise, as you're looking at quantified self meets end of life meets, and questions of whose data is it?
Right, right. No, these are really good questions, and I mean, I don't know, but the fun is trying to figure out how do we build the system in an intelligent and reasonably safe way, right? How do we determine how much of this biology can we really get ahead of? Thinking of things like Huntington's disease, if I can give you a diagnosis, you look like you're getting cancer, and I can't do anything about it, is that really necessarily something everybody wants? There's a lot of social judgment in how do we prioritize these things, and what do we get ahead of, and at what resource cost? And I don't know what that looks like, but it's things that we're going to be putting on the table in the next several years. And so I think that it's really important to raise awareness of that so that interested people can have that conversation. And before I run out of time, I wanted to just riff on something else. I was given, by you, I was given these blue blockers, right? So I think we've got 100 of these, anybody that wants one. The idea is, and I'm not advertising these, the idea is that blue light is the light that your retina is very sensitive to going to this central orchestrating clock in your brain, the suprachiasmatic nucleus, so SCN. And that's the orchestrator that's trying to keep the synchrony across all of these different flowing systems. And it's very sensitive to blue light because blue is the daylight sky, let's say. I'm sort of making that up as a why reason, but therefore, when I'm looking at my computer at night and I'm getting blue light off of it, I'm telling my brain it's daytime. And some of my brain, just the reason jet lag doesn't feel good, some of my brain can adjust fast, some of my body can adjust fast, some of them can't because it depends on the coupling, the interactions of these flows. There was never a historical context in evolution to say, now make everybody 6 hours earlier all of a sudden, right? So there is just no, as we were hearing last night, there's no stock for that, right? And so you instantly run out of your synchrony stock and you feel crummy until it gets back into synchrony. So there has been some research now saying, well, what if we just block the blue light, right? So then you can wear blue blockers like this at night and you can read your iPad and now you're fine, right? What I would argue is that research is real, right? That there is some effect of that, but I think it's just a sort of raising awareness point for the much larger issue that in the same way that we would want to take lead out of the environment once we realized it was causing us harm, we can't really take time out of the environment. We can't take modern infrastructure out of the environment realistically. But we do need to be aware that our temporal environment is also impacting our health. And city lights that come in through your bedroom window that therefore are disturbing your sleep by giving your brain daytime signals at night have a real health impact just like shift work does, just like urban noise does, just like all kinds of things that your body is taking time cues from. Eating at night when your body is expecting you to eat during the day and now your liver is jet lagged relative to your light-sensitive brain, right? So blue blockers is maybe a decent first step in some instances, but it raises this question, which we have no idea what the answer is, which is how do we manage our temporal environment so that it's working with our bodies instead of us just sort of banging ourselves against it and causing a lot of unnecessary ill health from that.
Essentially, are we saying that in all existing medicine, maybe not all, but overwhelmingly, temporal measurement of health and well-being does not exist, right? We just take snapshots, in whatever form it is.
Right.
So to what extent does this presuppose or pre-require what you're describing, an entirely new branch of, of medicine to be created?
Well, it really does, and it's appropriate to this conference because it requires a lot of this flow computational architecture. monitoring lots of people, enough people that you can get the heterogeneity and not just say, here's an average human, which is, in fact, nobody, right? How do we monitor that information? How do we pare it down to enough information that your doctor can look at it and go, oh, I see that these flows are perturbed in this way that I care about, and here's what we're going to do about that, rather than an ocean of data that you can't, the hairball problem that we heard about earlier that you can't interpret. And that's definitely not part of medicine. It's not part of education. It's not part of the culture. And how that grows is a very open question, right? I think it's really exciting. I think it's clear that there's reason to grow it. I think it's obvious. I mean, it's obvious to me, and I think it'll become more obvious to the world that there is a ton of good that can come from this. But as you've asked, right, what are the right biomarkers for which issues, for which people? How do we manage those flows? How do we keep them secure? How do we pare them down to something that is useful to a clinic, to a teacher? We have to figure that out.
It's curious, isn't it? Because in a way, some of this sounds so intuitive. I mean, we've known for years that shift workers get sick.
Right, exactly.
Anyone who travels the world, and I guess that includes about half the population.
I was going to say, I've talked to a number of people about, I'm feeling really jet lagged. What's that about?
Yeah, and it's not great for your long-term health if you're doing it all the time.
Right, that's right. And it's not good for your long-term health if you're in a sensitive period like puberty or early development. And so yeah, I mean, some of it I think is just a framing issue. Like you say, we've known for a long time that shift work is unpleasant and jet lag is unpleasant. Reframing that as there is temporal structure in biology and we need to understand that so that we're not, grinding the gears. It's just reframing it as a broader, more basic question, I think, rather than treating jet lag or circadian rhythms as a special case, right? They're just sort of illustrations of, we know a lot about, for example, down to the atom molecular structure of a lot of these hormonal systems, but we don't know better than 24-hour rhythm structure in time, right? Or maybe we know every couple of hours. The temporal resolution is lagging behind the spatial resolution in a big way. And the more we can fill that in, the better we can deal with these biological systems, which is, in fact, everything we care about. It's our psychology, it's our well-being, it's our world, right?
We're going to leave it there. Thank you very much indeed, Ben Smarr.
Thank you.